Hi everyone, I'm Saul. Today we're going to talk about speed without drag. But before, I've learned many things from James Powell. One of them is that, there's no such thing about as talking too much about yourself. So a little bit about me. I'm a Spaniard in New York. That's pretty obvious here. This talk was originally written for PyData Berlin, so that made more sense there. I did include a joke about a sing-song, Englishman in New York. Completely went over their heads. The Germans have a particular sense of humor that, I couldn't kind of grok. I did have a backup joke about soccer, about the World Cup. So I talked about the 7 goals they scored against Brazil. And that did get a chuckle, but that was it. I don't know about you, but I don't want to see what makes them laugh. My background is in electronics and computer science. And after I moved to the States, I worked first in AdTech, a company called Ampush, doing big data analysis and advertising, invading your privacy, you're welcome. And now I work at Thinkful. It's EdTech, and we're trying to reinvent education. More of that if you look for the Thinkful people that are around. By looking at this slide, I kind of think that my next job is going to be a challenge. I need a company whose name is a word, but not really. And then I need an industry that follows that pattern. I don't know if EDC tech, maybe, I don't know. Anyway, you can find me at that email if you want to send hate mail after the talk. You can tweet at me, definitely. And if you want to follow these slides, I just uploaded them to GitHub, to that repo. So let's get down to it. What's the story here? Why are we talking about this today? I like writing code, and if I have to write code, I much rather be writing Python than anything else. I don't know if that's a shared feeling around here. Who here likes Python? Okay. Who here loves Python? All right. I mean, it's Sunday. It's 9 a.m. I understand, but I also understand that if you're here, that's because you love Python. So who here loves Python? Yay. Awesome. All right. Who here has heard before? You can't do that in Python. Python's just too slow. Who has reacted aggressively to that? All right. By the time we're done, I hope I have given you enough arguments to counter that statement and enough energy so that you actually react aggressively. If you don't understand something, if you fall asleep throughout the talk, which I understand, just fight with your fists. It's Python, so it's all good. So yeah, the origin of the talk is, hearing people, usually people that don't really do Python, say over and over, well, Python's just too slow, you can't do that. And they always, for some reason, are JavaScript people. Doesn't make it any better. Okay. So we're going to talk about how to speed your numerical Python when there's no time to waste, which means when, you don't want to write C or Fortran or something else or Julia or who knows what. But first, because I'm from the north of Spain and this is something we do, I'm going to tell you not to do any of this. I'm going to tell you to think first and just do something else. Because there is no such thing as a free lunch, and in that same way, there's no thing as a free speed up. All these things are almost free, but not entirely. They come with their own set of issues. So think first and then don't try. That's pretty Spanish too. What if instead you thought things through and refactored things? Maybe what happens is you wrote that code in a rush and it's just poorly done. We'll talk about some ways of doing that later. Or this is actually Jeff Bezos' favorite solution. You throw money at the problem. You spin up 1,000 EC2 machines, and you're done. We've talked yesterday. We had a talk on pandas on Spark. You can do something like that, and you don't have any other problems after that. You can evaluate the cost of opportunity of doing something else, such as staying in bed instead of coming to hear me talk. And you can blame it on the jail and Van Rossum switch to Java. Let's just not. Okay. First, before you leave the confines of CPython, I would say rule out other problems before you try using something that's meant to speed up numerical code. You should probably make sure you have a numerical problem. Make sure you don't have I/O problems, which are really common. Deserializing, serializing, any other bottleneck that's not actually Python being slow because of the CPU bound part, I guess. Because these tools won't help you otherwise. I can't help you no matter what. I don't know why I wrote you. You might be calculating things over and over. Someone it's probably not me, was calculating a regular expression over and over not too long ago. Those things don't help you. You're going to be displaying an integer at the end of the day. Don't calculate floats. Don't calculate. Maybe you don't need the precision you think you need. Things as using different types of randoms can yield benefits without doing too much work. And many other things. There's a link here to a talk by a gentleman named David Sachta, who works in Silicon Valley somewhere. It's basically the opposite of this talk. He tells you what to do, going to the nitty-gritty details and basically writing C and examining what the CPU does and so on. It's a different approach. It takes much longer, but almost all of us are nerds, so it's rewarding sometimes. And of course, capture the low-hanging fruit in Python. Use multiprocessing. Take care that your overhead doesn't kill you. And Amdahl's law, which states that you can only get away with multiprocessing for so long. Make sure that doesn't kick in too early in the process. Check things like rebuilding temporary things or immutable objects such as strings. Python has some obscure features like slots. Make sure you're leveraging all those. Fast append comprehensions. This is a really well-known one. But for some reason, we tend to forget about it when we're doing numerical code, and instead we do loops. They do really help a lot. There's always generators. The ones of you that are from New York are pretty familiar with them, thanks to James Powell. But seriously, don't use his code. But that's not the point of a talk. The point of a talk is actually the opposite. The point of a talk is what libraries and tools can we use to, I wrote, circumvent the safety of Python. And it's kind of true, because what most of these things will do is circumvent some Python features that are there for your own good, such as type inference, not type inference, but duck typing, bounce checking, all that stuff that, when you can figure out when not to do it will speed up things. Many tools such speed. This talk is 5-6 months old now. This really feels outdated, so that probably means I should have chosen a new meme. But still, we're going to go over exhausting CPython, which is basically what we just did. SciPy, NumPy, Numba, Parakeet, NumExpr, Theanu, PyPy, NumPyPy, Jython, Blaze, Python, and Python. What are all these things? We'll talk about that in a minute. And the driving example for all of this is it's the only interview problem that I have, so do not tell anyone. But this is basically one of my favorite interview problems, which is build something to calculate the area of a polygon given its coordinates. Nothing too crazy. And before we start, a disclaimer. The measurements that we have inside the IPython notebook are what they are. They have been done in this machine, which is not a production server. We're just using the one case, which is the area of the polygon. So it's not a really good representation of what all the libraries are capable of. This is just, again, a driving example to showcase most of them, which probably means that some of them, this is not the best problem to address with them, and some of them are obviously benefited from it. In general, and this is one thing that came up in Germany, in general, especially if you don't want to work, if you don't want to write C, if you don't want to think about it, you really have to figure out what your problem is and what your problem will be in order to choose the one that will help you the most now and in the future without having to go back and forth or re-implement things. So let's go with the CPython vanilla implementation of this. First we need polygons, so I created this really nice piece of code that generates a list of coordinates for a polygon that's basically a diagonal, like those X's that I masterfully draw up there. The code is ugly, I'm not too proud of it, but it does work. Now, when you write code like this, if you're James, you turn it into a talk and tell people not to use it. I prefer to test it and call it production code. So that basically tests that the diagonal actually does what it's supposed to. And this is a solution to the interview problem. It's basically a summation of determinants of the array that contains the coordinates. If you want to look into it, it's Sunday, it's 9 a.m., your call, but if you want to look into it, this is the shoelace formula, which is also called Gauss something, which is a particular case of Green's theorem, which in turn it's a particular case of Stokes' theorem. Anyone awake yet? All right, and we test it. I'm going to sit down now because this is mostly code. And we test it, and it takes, for a diagonal that's 200,000 blocks or X's tall, we get 1/4 of a second in Python. All right, so now let's go over the tools we're discussing today. First we have SciPy. SciPy, as you know, it's many things. It's an ecosystem, it's a community, it's a stack, it's a library. As the ecosystem, it basically encloses most of what we're going to talk about: NumPy, Python, Pandas, PyTables. But it was also originally the name of a package that contains algorithms and scientific things. which won't really help us for our problem, but NumPy will. And NumPy, as you know, it's the library for n-dimensional arrays. That's being around forever, and it's battle tested, and it's awesome. It uses C and Fortran in the backend for speed, but you don't have to care about that, which is the great part. And it's technically, or it was, not entirely sure of how it works, but it's technically part of SciPy. Only you can install it on your own because it's really useful on its own. So let's use NumPy to address the example. And what we do after importing it, we create an array, a NumPy array. And by the way, I should have said during the disclaimer that all the uses I have of the libraries are okay, they work. Especially if you are familiar with NumPy, you will think of ways of speeding even the NumPy examples up. So again, the measurements are, useful, but you don't have to sort by them. Anyway, after creating the array, we basically create a solution which is the same, only using the vectorized forms of NumPy. We test it because we do that. The code might be ugly, but has to be tested. And just by using NumPy, and we didn't do much. I mean, we had to learn how to slice the array, but that's about it. We go from 1/4 of a second to 9 milliseconds, which is great. Next up is Numba. Numba is a just-in-time compiler that leverages the LLVM project. How many of you are familiar with LLVM? Okay, so LLVM is a huge project, really important project, open source project. It's something that is really key to open source these days. What Numba is leveraging is think of it as a C compiler of sorts. Well, it's a C compiler, but think of it as something close to a C compiler. What Numba is doing is analyzing your Python code. It's building the abstract syntax tree of your code. And then it is translating it to intermediate representation in LLVM, which is this thing that is code and that looks like code, but it's kind of weird. And that it's shoved into the LLVM compiler and optimizer. So basically, think of it as if we were turning Python into C and optimizing it heavily on the way there. It reads only a subset of Python and NumPy, so that analysis it does of the abstract syntax tree is not the entirety of Python, but it's the parts that you really want to speed up, right? So if you're formatting strings, you probably don't. Well, that's not entirely true, but if you're dealing with numerical code, you probably don't want to waste time trying to figure out how to optimize formatting strings. It has experimental CUDA support. You can statically compile it, which is kind of awesome. And it's a freemium open source model, so they have a commercial version that has multi-core and GPU support. If you're not tired of me yet, which is unlikely, I gave a talk on Numba a while ago, so you can go there and watch it. Well, those are the slides. Don't look for PyCon Spain, because obviously it will be in Spanish. But the talk was given in English at PyData New York last year too, so you can look for that video. So Numba, really easy to use. You just decorate your numerical functions with a JIT decorator. In this case, we're using it directly, but you can also decorate. And if we JIT the vanilla Python solution and NumPy solution, we get numbers that are not great. Numba chokes on the regular Python solution, or rather, it can't really speed it up, and it takes more time to get it through. And it speeds the NumPy solution slightly. This is not representative of Numba. depending on what you're doing, you will get speedups up to 1500x. So as I was saying, some libraries have better luck than others in using this example. One thing that's unrelated to the driving example, but that I wanted to mention because it's really cool in my opinion, especially if you use NumPy, is vectorizing. As some of you might know, NumPy lets you vectorize functions so that you apply them in a vectorized fashion. But it's just a helper to get your function to make it so that you can use it in that way. Now Numba has the same thing. Also, it also puts it through LLVM. So we have an example here of squaring something and adding 1. We're comparing it to the NumPy square function, and it's even faster than that. What you got to understand too is that NumPy has square, but if you have something else, and NumPy will probably, if you have something more complex, NumPy won't probably have a vectorized method for that, function for that. So really useful thing, really cool thing they did there. And again, anyway, going back to our, how am I doing time? So going back to our examples, we've got Parakeet, really similar to Numba originally. The development shifted into implementing stuff in C and OpenMP. They basically deprecated the LLVM backend. CUDA support, experimental too. The writer is here in New York, so I haven't seen him around, I think. Same thing, same kind of API. You decorate it with JIT. And this time, Parakeet will also choke on the Python implementation. But the NumPy one, it gets sped up to 1 millisecond down from 250. So what did we do? We did nothing other than add the decorator. NumExpert. NumExpert is a library written by my fellow countryman, Francesc Alted, and other people too. And what it does is it gets your arrays and it chunks them into blocks that are basically the cache width, so that the CPU is working at its max. It also has optimization to avoid temporary storage of calculations that are not final. Has support for OpenMP, for the vector math library in the math kernel, for the transcendent expressions, transcendent functions, which is like a algebra or not algebra thing. And it's not as complete as a Numba, but it's a really useful set of expressions, and it's usually 5 to 10x faster than NumPy. What we do is basically we define things we define the computation we wanted to do in a string, and it gets evaluated. The results are pretty good. We go from 9 milliseconds to 2.5, and we didn't do much work either, so it's great. If you're into that, the source code for NumExpert is something to be read. Probably not at 9 a.m. though. Theanu is a library that's really didn't fare that well with this example, but it's one of the oldest, I think, of all of them, and there's been a lot of work into it to get things to work on the GPU and using CUDA. Really specialized. It's a pain in the ass to install, or it was to me. Anaconda will solve it if you want to play with it. There are cells in this IPython notebook that are hidden to make it work. If you go on GitHub, you can see that there are some path tricks that you have to use to make things work. Nonetheless, you can tell by the vectors and so on how this is more geared towards the GPU kind of work. But again, we haven't changed the solution as much. You can see how it's basically the NumPy solution with the vectors. And while it doesn't best NumPy, it's faster than CPython, and the goal for this would be to use big data sets and parallelize things. So it's still pretty good. And then we leave CPython now, and we talk about PyPy. PyPy is a just-in-time compiler that follows the Python spec, but that is not what we usually think of when we talk of Python, or CPython rather. Kind of old, really mature, lots of support. It's not entirely seamless, the transition to PyPy, but it's really fast, it's really mature, it's really useful. In fact, so I'm also, as I said, I'm Spanish and I'm lazy. There's probably an IPython backend for PyPy backend for IPython. I basically chose to do this in the shell. So I created a shoelace.py, which has the same code that we saw earlier. And if you run it, just by running it in PyPy with no changes whatsoever, you can see the difference. That is probably around a 70x improvement. And PyPy, with some exceptions, should understand all the Python you throw at it. So that's pretty good. In fact, I think that's as good as it gets for today. There's NumPy. So if you had NumPy code that you had written for CPython, you can use it in PyPy. It's not as mature. If you go to that URL, you can see which things are supported, which things need work. But it's still a work in progress. There's a lot of effort that's being put into it, and it's improving every day. Unfortunately, what that means is that the normal PyPy version is faster than the NumPy version. But still, it's pretty cool that it works, and it still is faster than 10x faster than the CPython run. So there we have them in comparison, and I think there's another there's another slide there. So to compare these things, given that I left IPython and I had to go into the shell, I had to do this to test them, to test the previous solutions with NumPy and so on. And there's a slide missing, I think. It's at the end. Then we've got Jython. Jython is another Python. This time it's Python running on top of the Java virtual machine. It's less mature than PyPy, but it's still a huge project with a lot of backing, and it's pretty mature. There's no NumPy, so as you can see, the Python solution, the vanilla Python solution, is slightly faster than CPython, but there's no NumPy. Jython, again, should take most of your Python as well. One caveat to this is that 2-second number doesn't include the JVM warming up, or even like being launched, so that you have to take that into account. And this is the final comparison, which basically puts PyPy ahead for these methods. Again, grain of salt. It's just an example. Your mileage may vary. And then we've got things that are for the future that we can't use, and you won't see numbers for. Python is a new just-in-time compiler of Python 2.7. It's being developed at Dropbox, that recently hired Guido van Rossum. It's built on top of LLVM, so it's doing all these tricks that we discussed. But it's really, really early on. They basically don't support most of Python. There isn't an OS X version yet, so it's just work in progress. Yeah, that's unusable, but it's really promising. If someone was going to do this, it's either an open source project like PyPy or a huge company with a lot of funding like Dropbox. We've got Blaze, which is a library. That's the next step after NumPy and Numba. And it's a cloud big data infrastructure and analytics library. I kind of cringe as I say that, but it's really promising. It's going to be awesome in the future, I believe. You can go there and watch it grow. And then we've got Python, which is Python to C++ transpiler, which basically means what you think it means. It takes your Python into C++ directly. This is not using any tricks. It's literally taking your Python, examining it, and turning it into C++. Modern C++ too, so it uses SMD instructions and so on. Really complex and kind of young project, but really interesting to see how far they've gotten. There's a link to a talk there if you're interested, and that's how it looks like. The only thing you have to do is basically decorate the function with a comment. And when all else fails, C extensions, Python, C types, CFFI, and Ruby. No, not Ruby. All right. A gentleman called Sami Villar has written this same example in C in many ways, using SSE, using SIMD, using all the tricks he could, multiprocessing. You can go to that repo and see what he did. Turns out it's not as beautiful as the Python solutions, which is kind of the point of this talk. Hopefully you won't need to go as far as writing something like this. Props to Sami, because it's a lot of work, and it's actually, I believe, 10x faster than the best solution I have. But that 10x faster comes at this price. So to recap, no free speed up. So think again and don't do it. And if you're going to do it, make sure you use the best tool. You've heard about many. Choose the one that suits your use case best, while using the second best tool for any job, which is Python. How corny is that? Thank you. I think we've got like 1 minute or so for questions. What are the safest for production use?
Yeah.
Good. I would be inclined to say anything that comes with Anaconda, which is most of them, because that way you can just throw Miniconda or Anaconda in and forget about it. In general, that's why I say there's no such thing as free speed up. When you choose these things, you basically have debt, and you will have to explain the next intern why that code is there and what it does, and what LLVM is and all that. And then deployment-wise, they're not immediate. The ones that are, GPU for clusters and so on, like Theanu, have their own set of problems for deployment. The ones that are less like that, say NumExpert, still they have their, even SciPy, even NumPy. Deploying NumPy is not immediate if you want to do it manually and you haven't done it before, and if you want to compile it on the server. So, use Anaconda. That would be helpful. Or NumPy is pretty easy to deploy. Some versions of Numba are. NumExpert is okay, and that's all I got. But yeah, in general, you'll find that while speeding it up on your local, it's easy. You're gonna have to track all those things with you. So.
Can you talk a bit more about PyPy? Why is it so much better?
It's an entirely new interpreter, so it's not, and it's a just-in-time compiler, as opposed to, so yeah. there's more to it. There's a lot of work that goes into it, but mostly I think it's the just-in-time nature, and the fact that they came after the fact and they knew many tricks, I guess.
So sort of a comment and a question. The comment is just on PyPy. PyPy is really great for certain class of problems, but at least the last time I checked, basically C extensions don't work, right? So this is why you have NumPy, which is an attempt to rewrite NumPy for
Exactly.
PyPy. And so all of the other stuff in the ecosystem that, scipy.special, scipy.stats, all of this stuff, you basically are going to have a hard time using, if I understand correctly. And I guess the question is just, the example you showed was essentially sort of a question of trying to write a tight inner loop, right?
Yep.
Which is why something like PyPy does really well there. And why something like Piano those are like completely the other end of the spectrum with the problems they're trying to solve. I was wondering if you could just kind of quickly comment on, I guess, the kind of where you would suggest one over the other, right? So tight inner loop, if that's all you have, PyPy is great, right?
Yep.
There are other situations where other tools might be more appropriate.
So yeah, that's a good qualification. PyPy won't take many libraries that have C functions of any sort. And then when to use PyPy, when to use Theanu. I would use PyPy when you have like a already written code base that's Python, and that's just Python, not anything else, and you want to not do a lot of work. I would use Theanu when I have a big data problem and I can basically work a little bit more into actually getting my problem into Theanu and using, obviously, this was not the best example for them, using their capabilities of GPU and clustered computation. So more scientific kind of work, definitely. Analytics, offline analytics, that kind of thing. While PyPy can speed up, CGI computation that you need to deliver online for some reason. That's that. I think that's it. Cool, thank you.